simplest example is we take n to be the real line, n to be the origin. What is the distance function from a point to the origin in the real line? It's mod x. Mod x is not differentiable, but if we square with x squared, that's very nice function. It's differentiable. In fact, it's more because it's f of x squared. The origin, if you differentiate the Hessian, it's 2. It is a Morse function. But of course, your n need not be an isolated point. It could be a submanifold. So you could imagine a similar phenomenon happening. Right? N could be, for example, the x-axis inside R2. What would be the distance function from any point on R2 to the x-axis? Well, take x comma y, and you're simply measuring the height, the y. Then you're taking the square. So x comma y goes to y squared. That's the function from R2 to R. And the entire x-axis is going to be the critical set. We have seen that in the very first talk. So these are included. So these oftentimes give you more spot functions. But you have to be a little bit careful if your n is compact, n is closed. Because in the R2 example, m was uncompact. So the idea is that m is wide. And I will say what I mean by wide. Quite often the answer is, in fact, always, but you cannot define it on all of it. You remove certain things, and then that mu f on the smaller subset of x turns out to be a more small. And we'll see in a couple of examples. But keep this in mind. This is a fairly standard function you'll encounter even outside of the course. This n equal to the submanifold. This will be a closed set, and you're trying to build some path, avoiding n and more to optimize this. So people in other areas like calculus and variations. Okay, so let me give a few examples of what this thing looks like. First on M, which is like Rn or unbounded, and then on M, which is compact, so that you'll see a difference. In the sense, sometimes you have to remove certain things, sometimes you don't have to remove anything, and the original f is more. So then, the natural question then would be, what is it that I'm removing? And is there a description of what I'm removing in terms of geometry? It's not just you remove something to make your function. Again, let's say example of watch it. This is more examples. This is like the introduction, the example that's sorry. Let's start with the simple example. This is n is the equator and m is the 2 square in the equator. You can do the same thing for any approximate Sn in Sn. We related to that last example. Okay, so here, what is the distance function? And you're saying, even, sorry. This, and given any point, sort of have to measure the distance. So if you imagine this doesn't look like a north pole, and so given any point P here, literally look at the red circle joining the north pole at this point, and wherever it hits, this is the length you measure. That's the distance from the equator. So if you are here, you do the same thing. So the distance from any point to this thing is at most pi by 2, because this is a unit circle. So this is pi by 2, that's pi by 2. So if you, so what you want is you want to understand d squared with respect to the equator. And so if you think about it, so this is the crucial return was at f mod So why is it the case? So the point is we are claiming that the function is not differentiable at the pole. So in particular, that would mean that if you are at the pole and you are choosing a tangent direction, to differentiate this function along that direction, the derivative does not exist. And that's because what happens if you go across the pole? See, if you are here, if you go across, the distance is actually going to be measured from that side. Because if you choose a small curve passing through the pole, let's say this one. If you go beyond, the distance from this point to the equator is this one. Whereas if you are here, the distance is measured here. So when you write down f around the pole, it sort of looks like a version of, it's not mod x, but it looks like a version of, like you get t squared and t squared as t goes to pi by 2, and on the right hand side you get pi minus t whole square. So that is of course not differentiable at t equal to pi by 2. So it sort of has this fluctuation. So the same thing happens here. So this is not not direction differentiable at either of the two poles, but otherwise it's a perfectly fine function. So you can't even say that okay, is this a more spot thing, or if you remove the points where this is not differentiable. If that set of points where this is not differentiable is not closed, then to remove its closure. But here it's convenient that these two isolated points are close, so but to remove something, so here we remove 0, 0, plus minus 1, and then it's an easy thing to check that S2 minus S0. This is still the same function, right? F restricted to this is what? And what would be the critical set? You're removing this and removing this, and then looking at the system squared function from any point to the equator. So any guesses what the critical set of this would be? This is now an open matrix. It's not quite z squared, but sort of up to, think of z as cosine t, cosine theta, sine theta 0, and sine t, then it's like sine t. Because the z square would mean the literal vertical distance, but this is like arc cosine of it. Almost like z square. So as we know, z square, the entire equator has to be the critical set. Critical, so let me call it that. It's the equator. So now we should take a step back and think, well, is there some reason why we're getting this, or is it just a coincidence? Well, from basic topology, we know that if you remove the 2 poles from the sphere, that deformation retracts to the equator simply by flowing down, flowing up. Because if you remove the 2 poles, then that's essentially a cylinder. You can collapse a cylinder to the equator. So if I remove the 2 poles, this one, I can take any point and simply flow it down along this and get a deformation retraction. So the equator is a deformation retraction of S2 minus this. And this should be reminiscent of what happens even in the basic Morse series setup. That if you encounter the first critical point, the minimum, if you go up a little bit, it looks like a disk. And the disk deformation retracts by the flow to that. If you have one critical point, everything will have to flow to that or flow down from it. Nothing else can happen just by the equal coordinates. This is saying that if you remove the 2 back points, globally this will deformation retract to that. That we already knew, but you can capture that also by the flow of this terminal geometry. There's a connection that this is not just by coincidence. This will deformation retract to this, either pictorially or by exposure. Once you remove the 2 points, then it's not exposure. Okay, so what about the other example? Other meaning, now I switch sort of sides. Rather, I switch the f and the this thing. So I should do that. So it's one p, one p. So now my n is going to be, as you can imagine, this is S0. So it's a rather benign submanifold. There's 2 points isolated, one not full, the other was submanifold. We'll do the same thing. So F is so here again you can check that F is equal to S2 minus. The equator is going to be sort of the bad one, where you lack differentiability of them. To remove that, you still have a function. This is just a restriction. And the critical set or the critical locus is this. Again, what is this saying? If at all it's saying anything, it's saying that if you